evaluating an iterated integral over a type 2 region. That's what example 5.13 shows us. We're asked to evaluate the double integral over the region D under the function 3x squared plus y squared. And we're told that D is the region of points x, y, such that y is squeezed between the constants -2 and +3, and x is between the functions y squared minus 3 and y plus 3. Now, if we tried to graph these, we could see that this region, in fact, can be described as either type 1 or type 2, but we want practice with both, and since we've already seen a type 1, let's try doing this one as type 2. Another argument for why we should set this up as a type 2 region is because type 2 regions have our x values between functions. So if you already see x between two functions of y, you should automatically assume type 2 would be the easier route. That's not always the case, but it's just a good general rule of thumb. So if I just sketch this graph for you, our y squared function is going to look a little bit like this, and then the y plus 3 is going to look like this. So the region D is between those two curves. The y squared function, that was y squared minus 3. And then, that x is too close to that. Let's write it again. And then our linear function, that is the x equals y plus 3 side. And so in a type 2 region, we draw our horizontal lines across the entire region. And then we take note of the fact that y ranges from that bottom point, that's y equals -2, and then the top point, that's at y equals +3. And if you weren't sure about how to find those, remember you would just set the two equations, y squared minus 3 and y plus 3, set them equal to each other, and you'll find the intersecting points at -2 and +3. All right, we are ready to set up our double integral. Because we're doing this as a type 2 region, we're going to integrate with respect to x first, y second. So let's go ahead and set up our integral. I'll copy the function into the integral first. Then we'll replace dA with dx dy. X being the inside part means that inside integral is going to have the functions x equals y plus, just kidding. The smaller value for x is the y squared minus 3 function. The larger value for x is y plus 3. Remember that x is smaller as you go to the left, x is larger as you go to the right. So our left function was the y squared, our right function was the y plus 3. Then we need to do the second integral bounds, which are the y values. Y at its smallest point is -2 in this region, and its largest point is +3 in this region. And then we're ready to integrate. First, we'll work on that inside integral with respect to x. So I'm going to highlight that here with our green brackets, and then we can do some scratch work on the side. So let's copy that down. X only appears right here. The y squared we'll look at as if it were a constant. So when we integrate term by term, 3x squared becomes 3x cubed over 3, and y squared becomes y squared times x. And we're going to replace our x's with the bounds y squared minus 3 and y plus 3. Now, this is another reason why I think it's super important to write out that your bounds are either x equals or y equals, because when you go to plug them in, it's easy to get confused about who's being replaced with what. Another thing that we can do to try and make things less messy is simplify what we have from our integral the best we can. So let's divide our 3's off, and then also notice that we can factor the x's so that we're plugging in x's in fewer places, although really it's not going to make much difference here. But if you wanted to, you could factor x times x squared plus y squared, and then evaluate that from x equals y squared minus 3 up to x equals y plus 3. So then we'd have y plus 3, well, not 13, y plus 3 times y plus 3 squared plus y squared minus y squared minus 3 times y squared minus 3 squared plus y squared. And then we'd want to clean this up the best that we can. All right, we've cleaned all of that up so that we can now integrate this all with respect to y. Now, looking back, remember how I had said that in a type 1 region, you need to integrate with respect to x first so that you can eliminate all of the x terms. We started off with x terms, we integrated them out, and then after all of this gnarly algebra, it gets worse than that, I'm sure, but notice that we're only left with y's. And now we're ready to finish this off by integrating our y values. Y was allowed to go from -2 up to +3, and we're integrating that 54 plus 27y minus 12y squared plus 2y cubed plus 8y to the 4th minus y to the 6th. And luckily this is just a polynomial, so it's not going to be too bad. However, there are fractions involved, folks. Don't be afraid. I am going to jump to the end, though, because I know that we're all very capable of doing this, and even if we weren't, it is in your textbook. You can jump from here to the end, and if you aren't comfortable with that, you can see the in-between steps because they're spelled out quite nicely in the book. But the final answer is going to be 2,375 over 7. So after getting a common denominator, that's the end result there.